If we are given sets, we can form new sets from them by applying operations to these sets. So if you give me two sets, I can form a new set from them by applying some operations to them. Some of the most commonly used operations or defined operations are what we are going to show in the next few slides here. So one of them is the union. If you give me two sets, A and B, the union of A and B is the set that contains all the elements that are in either A or B. Okay. Now remember that an element cannot appear in a set more than once. So if an element is in A and in B, we list it only once. If we want to use the Venn diagram to denote the union, again, I draw the rectangle for the universal set, and if this is A and this is B, the shaded area here is all the elements in the union. So if we want to show examples, if A is 1, 2, 3, and B is 2, 3, 4, 5, then the union of A and B is the set of all elements that appear in either A or B. 1, 2, 3, 4, 5. Okay. If we look, for example, at A being the empty set and B equal ABC, then A union B is the set of all elements that are either in A or B, that is ABC. This is the union of two sets. Okay. The intersection of two sets is the set of all elements that are in both A and B. In Venn diagram, if you look at two sets, A and B, this is A and this is B, then the shaded area that corresponds to the intersection is this one here. Okay, so the elements that are in both A and B. So if we take, for example, A, the set A, B, C, and B, the set B, D, E, then A intersection B, what are the elements that are in both of them? Just B. Okay. If I take the set A, B, C, and I take the set C to be D, E, F, the intersection of A and C, what are the elements that are in both A and C? Nothing. It's the empty set. Okay. In particular, if you look at the intersection of the empty set with set A, no matter what A is, you will find that there are no elements that can be both in A and the empty set because the empty set has no elements. So this is always empty. Okay. Now, if the intersection of two sets is empty, that's what we call two sets being disjoint. Okay. So if I look at two sets A and B, and their intersection is empty, what's the Venn diagram that corresponds to this situation? If you look at U, this is A and this is B. There are no elements in common to both of them. This is when we call A and B being disjoint. Okay, so when someone says disjoint sets, it means that the two sets have no elements in common. The third operation we are going to talk about is the difference. The difference is that we are subtracting one set from the other. So if I say A minus B, which we use one of these two notation, either A minus B or A backslash B, it's the set of all elements that are in A but not in B. So if I look at, again, the Venn diagram, and if this is A and this is B, and you think about what are the elements that are in A but not in B, these are the elements. This is the shaded area here. Okay, these are the elements that are in A but not in B. So if we take, again, A to be A, B, C, and B to be C, D, E, then A minus B are the elements that are in A but not in B, which is A and B. Okay. In particular, if I take A to be whatever set and I subtract from it the empty set, this gives me A because I am removing no elements from A, right? So A minus the empty set is A. And also if you think about it, if we have two disjoint sets, so if the intersection of A and B is empty, this implies that A minus B is A, right? Because if they are disjoint and I want to remove all the elements from A that are also in B, then I'm not removing any elements because there are no elements that are in A and in B. Okay, so this is the difference. Notice that the difference, it matters whether we are talking about A minus B or B minus A, okay? Then we have the complement. The complement is always taken with respect to the universal set. So when we talk about the complement of a set A, I'm talking about what are the elements that are not in set A. So this is why it's important to keep in mind what is the universal set we are talking about. Because if I say, for example, what is the complement of the set 1, 2, 3, this is not well defined until I tell you what is the universal set, right? Because what are the elements that are not in this set? Well, if the universe I'm talking about, the set U, is a set of numbers 1, 2, 3, 4, then the complement of this is just 4. This is assuming U is 1, 2, 3, 4. Okay? But if I am talking about the set of all integers, or let's talk about the set of all natural numbers, then I talk about what is the complement of this. Well, the complement of this, if the universe was the set of all natural numbers, 0, 1, 2, 3 to infinity, then it is 0, 4, 5, 6, and so on. This is again if the universal set was n. Okay? When we want to draw this in terms of Venn diagram, and I have this set U, and this is set A here, then what's the shaded area that corresponds to the complement? It's everything in U that is not in A. Okay? So this is the Venn diagram for the complement. And if you take the complement, for example, of the empty set, if you take the complement of the empty set, it's every element that's in the universal set that's not in the empty set. So this gives you now the universal set. Okay? So this is what the complement is. And the last operation I will talk about is different from the previous one in the sense that this operation now gives us elements that are not in the original set in terms of type. So the Cartesian product of two sets, and there's an order of them. So when I say A times B, is the set of all pairs, x, y, such that x is in A and y is in B. So if I look at A being AB and B being 0, 1, 2, for example, then A times B is the set of all pairs where the first element in the pair, the one on the left, is from A and the second is from B. So the pairs I can form are A with 0, A with 1, A with 2. Or I can form B with 0, B with 1, and B with 2. Okay? Again, notice that the order matters here because these are what's written there inside the set. For example, this parenthesis A comma 0, there's order there. A comes before 0. If I wanted B times A, it becomes 0A, 0B, 1A, 1B, and 2A, 2B. And notice in this case, A times B is not the same as B times A. They don't contain the same elements here. Okay? So A times B is the set of all pairs that you can form by taking one element from A and one element from B in that order. In particular, if I take, for example, the empty set times A, for whatever set A, then I need to ask now what pairs can I form by taking one element from the empty set and one element from A? Well, are there any element in the empty set? The answer is no. There are no elements. Therefore, the empty set times A equals the empty set. And this is the same as the empty set, the A times the empty set as well. So the Cartesian product of an empty set with any set is always the empty set. Okay? And these are the central operations that we usually deal with, but we can again define any operations we want by taking a combinations of unions and intersections and so on.